Oh, you were on the colder one. Okay, yeah. I guess I can show the first question so you guys can match it up. If that's your first question, you're on the right one. Yeah. Are you recording right now? Okay. So now that we have recorded, we can start. So someone said error bounds. So let me check real quick if there are any good error bound questions. This might have some error bounds. Just checking real quick. There's a question. If anybody has an example of error bounds, feel free to.
Error bounds aren't necessary. There is, in the exam packet, there's separation of fractions, which is equally difficult for me.
Okay.
Separation of variables.
Separation of variables, all right. So I guess maybe this one. Like, can you even use separation of variables in here? No, that one.
I believe question 7 on the packet you have should have separation of variables.
Yep, thanks. I guess I can start here. And while I'm working on this, you guys can come up with other questions too. Okay. So since separation of variables was a question, let's go over this one. So here we have dy dx is equal to 9 minus 2y. So we don't have an x over on this side, but we do have our y. And we can't just add 2y over because then we have 2y plus dy dx equals 9. Then if we were to try to get the dx over, we'd have 2y dx plus dy equals 9 dx. That doesn't really work out because we have our y with our dx. So what we do instead is we take that as an entire group, so 9 minus 2y, and we're going to divide both sides by it. And then at the same time, we're also going to multiply by dx on both sides. I like to just combine these steps. So that cancels, and we get dy over 9 minus 2y is equal to, so this becomes 1 and then dx. So this is fairly straightforward here, but then once we try to solve for y, it gets a little more complicated. So we integrate both sides. So this is the easy one. Integral of dx is just x. So you get x, and then you do your plus c. Always do your plus c on the side with the x. And then here we have a 1 over linear function. So this will actually be a natural log for the integral. So we know that the bottom stays the same as the inside. So natural log of 9 minus 2y. You could also do u substitution on this as well, if that helps. So in that case, our u would be 9 minus 2y. Our du would be -2, or -2 dy. So since we don't have a -2 here, we have to divide by -2 or multiply by -1/2. Or I guess that won't show up there. It would show up here. And there we have our full equation right now. We want to solve for y though. So the way that we do this, so you want to keep your plus c throughout all of this. So first we can multiply by -2. So we get natural log of, so 9 minus 2y, it's equal to -2x. And now here we'll have plus c times -2. And because -2 is a constant and c is a constant, we can just simplify it back down to still c. So, because if we have 2 times 3, we get 6, it's another constant. C can be anything, so we can just shorthand this so we don't have to make it look messy. And then now, since we have a natural log on this side without any coefficient on the outside, we can raise both sides to the e power, or well, e to that power. So e and natural log cancel. And now we have 9 minus 2y is equal to e to the negative 2x plus c.
Somebody's asking about how you got -1/2.
Oh, -1/2. So here I used u substitution. I guess I could show the full work. So here you would have u is equal to 9 minus 2y. And so du would equal -1/2 dy. So since, or wait, no, it would be a -2 dy, my bad. -2 dy, since we don't have a -2 in here, we have to divide by -2, so we get dy is equal to -1/2 du. So then our integral would become, so -1/2 on the outside, then du over u, which is the natural log of u. So we get -1/2 natural log of u. U is equal to that, so that's where we get this entire thing. Yep. All right. So then from this step here, our 9 minus 2y is equal to e to the -2x plus c. We can, I guess first, if you want, you can simplify this bit. Since we have e to the -2x plus c up top, you can separate this into 2 different exponentials. And that's using the power rules. So we have e to the -2x times e to the c, because when you multiply 2 of the same base, you add the powers. And because e is a constant and c is a constant, we can again simplify this to just c. So we can get c times e to the -2x. So now we have 9 minus 2y is equal to ce to the -2x. We can choose to either add 2y, subtract that over, or subtract 9 over and then divide by -2y. Either case works. I'm gonna just do add 2y over, subtract this over. So 9 minus ce to the -2x is equal to positive 2y. And now, again, so this you can either keep the negative or make it positive. I don't think you'll get marked wrong either way, because again, c can be anything. But now we just divide the 2 over and we get y is equal to 9/2 minus, again, c divided by 2 is still c, ce to the -2x. And that would be the final answer right here. Any questions on this? Wait a bit. Yeah, the key has plus c instead of minus c. Either way works. So if there are no questions on this portion, I can go to the next bit just for a little extra practice. So again, here, this time we have an x to the 5th and then y. So we'll actually have to deal with the actual function of x instead of just 1. So again, y you divide over. So you get dy over y, multiply the dx over, is equal to x to the fifth dx. So from here, you then integrate. This one's quite straightforward. We did it up here. It's just natural log of y. And then the integral here is going to be 1/6 x to the sixth.
I had a quick question.
Yep.
When handling a dy or dx over y or x, is that treated as if it's the value 1 over x? Is that how you come up with ln y?
Oh, yeah, it would be the same. So you could write it also as natural log of 1 over y dy. You'll just often see it shorthanded into this form.
Thank you.
No problem. And then, so where I left off, so you took the integral up here. Again, always remember to put your plus c with your x term. It just helps out more. And then, so here it's straightforward because natural log of y is the only thing on the left side. So you just raise both sides to the e. And we get y is equal to, so we get e to the 1/6 x to the sixth, and then plus c. And again, what I showed you right here, we can simplify this plus c and just move it down to the bottom. So you probably will eventually get this down and you won't really show your work as often anymore when you see that plus c. This is a good thing to memorize right here, because it definitely makes it look nicer than having a having addition in your exponent. So yeah, that's the final answer there. Any other questions that you'd like me to go over?
To be clear, you took the c out of the exponent and then you're multiplying the rest of it by it?
Yes, and that's because again, up here, we went from e to the negative 2x plus c is equal to e to the negative 2x times e to the c. And since e to the c is still just a constant, we can just put it out front as c again.
Okay, I was trying to figure out why there wasn't a second e.
Yeah.
Once again, thank you.
So setting up an integral to compute the areas of surfaces. All right, yeah. Let me see if there's any good example up ahead. Or I guess it'd be back if it's going in chronological order. It's Euler's. And equations. All right. Yep. Okay. This one right here, 4. So this one, setting up an integral. So we are computing the areas of the surfaces obtained by rotating the curve specified about the x-axis and the y-axis. So we're given the curve y equals e to the x, and then between the points 0 and 1, and then 2 and e squared. So rotation about the x-axis. So I like to make visuals for this too, kind of helps. So we have e to the x goes something like this, though probably goes a lot higher very quickly. And we're rotating it about the x-axis, which is here. So we get an arc like that. So for this, we can imagine it's split into multiple different circles. And here the radius is going to be equal to our y coordinate. Since it's equal to our y coordinate, we know that y is equal to e to the x. All right. So then setting up our integral, we follow the integral for surfaces like this is, so we're going to take the circumference of many circles, so 2 pi r, and then you multiply by the arc length bit. So that's 1 plus dy dx squared. And then we want it in terms of x. So here our r is going to be e to the x. So we can start substituting stuff in. We know that dy dx is just e to the x again. So here we get 2 pi r, or 2 pi e to the x, times the square root of 1 plus e to the 2x. The reason why we can do this is because we have e to the x times e to the x, which we know we can do addition. So we get e to the x plus x. X plus x is 2x. And so that's setting up our entire integral, minus the bounds so far. Now for the bounds, since we're doing it in terms of x, we have to use our x coordinates. So since we're going from 0.01 to 0.2 e squared, that means we're going from x is 0 to x is 2. Does this make sense so far? I'm gonna take that as a, yep, okay, yep, got an affirmation, so good there. So now going about the y-axis, we have to change things up a little bit. So again, I like to draw my figure. So here's going to be a little different. And that's because we have e to the x, and we're going from 0 to 2, so we won't have like this little bit there. So we have that. And now we're rotating around the y-axis. So we'll go something like here. It looks kind of like x squared, but that's just because of how most parabolics and exponentials look. So then here we're going from, or well, what was I thinking? Okay, so here our slices are going out this way. So now our r is equal to our x coordinate. And we want this in terms of dy. Or, well, okay. Trying to think. There are a number of ways to do this. And I'm trying to remember. Okay, so I like to just set this up at least. So if we do r equals x, which is equal to natural log of y. Now when we set up the integral, we do, again, we still use this form. If you want to change the dx on the outside to dy, you also have to flip this. So you take the derivative of x with respect to y. So you take this derivative instead. You could also, I believe, do, so we could keep it in terms of x. And then instead of e to the x here, we would actually just have x. Then we'd keep that. And then our bounds would also stay the same. Yeah, because we'd still be in terms of x. But I'm going to show you how to do it in terms of y real quick, just so you know both ways. So here we can do 2 pi, and then our r is natural log of y. And then it's times the square root of 1 plus, and now we take the derivative of this with respect to y, which is 1 over y, and then square it. And then this will be dy. And now we just do our bounds, which is from 1 to e squared. And for those with their calculator available, you can test to see if this is true as a little exercise. So because we have our r is also equal to x, we can do this in terms of x. It would be from 0 to 2. And then our radius instead would be x, because we're using this equivalence. And then we have to use our dy dx squared, which would be, again, this bit. So these two should theoretically be the same. If you check that on a calculator, I think you'll find that I'm right, if I remember things correctly. Do I remember things correctly?
So,
Okay, yeah. I don't always trust my memory, but for this, I'm pretty confident. Does this make sense to everybody? So technically, either of these should work. Let me check if I actually have that on the key. I always forget that I have a key in front of me. Yeah, both work. Actually, the key has this answer on it. This should also work though. Yeah, the surface rotated about the x-axis is equal to this. Surface rotated about the y-axis is equal to this. And it will often help to actually draw out a figure like this so that you can see what your radius is exactly. Good practice. Any other questions?
speaking of,
I think we did this. I was like, I'm pretty confident that I learned this back when I did surface integrals. Oh, wow, it's only 6:26. Time is not flying. Also, keep in mind that this problem specifically said just setting it up. I don't know if they'll give you one where you actually have to solve it. I'd assume that if they did, it would be a relatively easy integral to compute. So definitely not e to the x, because I don't think you can compute this by hand. At least not given the formulas that we know. This one especially. No other questions? Everybody still thinking of something? Nobody wants to go over Euler's method?
I have another separation one.
All right, I take it it's not on the key? Or not on the.
It is not on the test, no.
All right, I'll just flip over one of these sheets then and we can work on that.
And if you'd like, I can put it into the chat.
Yeah, sure. Or if you want to speak it, I can. Either way works.
All right, it's dy dx equals 3x e to the y, and where y of 0 equals 0.
Okay, so this has an initial condition. So we can do that too then. All right. So for this, again, since it's multiplied, it's kind of fairly straightforward. You want to move the y term over here and then dx over there. So since we have e to the y, we can multiply both sides by e to the negative y. We get e to the negative y dy is equal to then dx over 3x dx. So now we integrate both sides. This is going to be messy manipulating the c and solving for y, so you can understand any struggle with this problem. So here, since we have e to the negative y, we have to use substitution. I like to shorthand it when it's as simple as this, because it's just a negative y inside the function. So we get negative e to the negative y is equal to, and then this is just your power rule again, 3/2 x squared. Don't forget the plus c. Now comes the hard part. So we have a negative here, so we want to immediately resolve that because we can't take the natural log. So when we do that, we multiply both sides by -1. This is a plus c, so it doesn't really matter. It's not really affected because c can be anything, well, any constant. So now we have e to the negative y is equal to -3/2 x squared plus c. And now we take the natural log of both sides. Natural log. So natural log of this, there's a power rule for logs. And that's if you have a power here, you can move it to the outside. So that becomes just power of 1. E to the first power inside a natural log is again just 1. So that cancels. So you get -y is equal to the natural log of -3/2 x squared plus c. And then because we have a -y, we want to solve for y. So we just, again, multiply by -1. So you have negative natural log of -3/2 x squared, and then plus c. So now we use our initial condition, and we have y of 0 is equal to 0. So x would be 0 in this case. So we get 0 is equal to natural log, or negative natural log of 0 plus c. So here we have to figure out what c value makes this all equal to 0. And that would just be 1. The reason why it's 1 is because e to the 0 power is equal to 1.
This one you do.
Oh, yeah. That's the first step, not the key. So, yeah, so here we just say c is equal to 1. That resolves it. So now we have y is equal to negative natural log of, so we can do 1 minus 3/2 x squared. I like to reorder it because I hate having negatives on the left. It's just a personal preference. And it also kind of helps you see how the function works, because this becomes undefined at certain x values. Does that make sense to everybody? Yep, natural log of 1 is equal to 0, and that's why c has to equal 1.
That's so it meets the original initial condition of y of 0 equaling 0.
Correct.
Okay.
And so that's what we were solving right here. Because in this case, so you have 0 equals the negative natural log of c, because the 0 just move out. And then we know we e both sides. So this cancels. The negative also kind of, the negative doesn't matter because it's 0. So you can kind of just cancel that out anyway. So we get e to the 0 is equal to C, key to the 0 is 1. So C has to equal 1. So any other questions? Can you do a slope field? Okay, let me see if they have a slope field on this. Oh, that's Euler's, which is close, but not exactly a slope field. Yep, make a rough sketch of the slope field for the ODE you found above. Okay, so I'm gonna have to probably work through this entire problem. All right. Oh, yeah, sure. I like that. Okay. So consider Newton's law of heating and cooling. So we get our differential equation right here. If the ice cream initially warms at a rate of 80 degrees Fahrenheit per minute, what is the value of K? So here we can just quickly use this. And so we have to use this knowledge too. So the freezer is kept at 30 degrees Fahrenheit. Oh yeah. So that would be the temperature of the ice cream. And then it's taken to a room which is 70 degrees Fahrenheit. So our TE in this case is going to be 70. Our T is going to be 30. And we're going to try and solve for K. So we know that, oh, and I guess I should also say dt d little t is equal to 80. And this is positive because it says it warms, which makes sense given that the environmental temperature is higher than the temperature of the object. So we get 80 is equal to K times, and then it'll be 30 minus 70. So this is 40 right here. And then 80 divided by 40 is 2. This is actually negative 40, I forgot, because it's 30 minus 70. And so K is going to be equal to negative 2. And then this will be a, it will have units. And so this is in temperatures, this is in Fahrenheit, this is in Fahrenheit per minute. So K has to be in minute to the negative first, or 1 over minute. So this would be your answer here. And then using that, we can solve an initial value problem for the temperature of the ice cream. So we know that at time equals 0, our temperature is going to be 30 degrees Fahrenheit. And we're going to solve this for T in terms of T, or in terms of time. So this happens to be, okay, so you get dt over T minus T environment is equal to K dt. So then taking the integral of both sides, we get natural log of T minus TE is equal to K little t plus C. Take the exponent of both sides, and I'm gonna kind of shorthand this. So we know that this will cancel and we'll have T minus T to the E. This will become E to the KT plus C, which becomes C E to the KT. And then we can move this TE over, get TE, and then plus, yeah. TE plus CE to the KT. And so we know our K, we know this, and we know an initial value. We can solve for C. So we know T is equal to, and then 70 degrees plus C E to the negative 2T. And then we know that at T equals 0, our temperature, or so at time equals 0, our temperature is 30. So we get 30 is equal to 70, and then plus C, and now E to the negative 2 times 0 is E to the 0, which is 1. So we just have this. So we know C is equal to negative 40. So now we know T is equal to 70 minus 40E to the negative 2T. And now, knowing that, we can make a rough sketch of the slope for the ODE you found above. So for 0, or so T, our time is from 0 to 10, and our temperature is from 0 to 250. Ooh, that's a, ooh. Okay. So here we're using our slope field, so we're going back to this equation. So you have dt. Oh wait, did I do that wrong? Oh, set up an initial value for the, maybe I didn't need to do all this. Ah, yeah. Yeah, this would be the much deeper problem. So that you would just do, if you're looking at the key, yeah, you just set up this right here. Wait, it's that minus 70, yeah. So yeah, my bad there. So this is what you use in order to solve for the slope field. So knowing that, we can make some tick marks. It's going to be very crude. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 250, I got to figure out how I want to do this, I guess. 25, 50, 75, 100, 125, 150, 175, 200, 225, 250. Okay. So now this is our temp. Oh, I need to slide up, yeah. I realize I have the screen right in front of me. Don't look at it. All right, so here's our time. So this is from 0 to 10, again, 0 to 250. So what we need to note is that we have, some equilibrium points. Well, actually, I think we only have one. And so that's the first thing you want to do when you do a slope field. You want to solve for the equilibrium. So where is dt equal to 0? So if we know that it's equal to negative 2 times t minus 70, we know that when t is equal to 70, dt is equal to 0. So we find our 70, so that's 25, 50, 75, so 70's right around here. So we'd have just kind of straight lines like this. And now after that, we have to determine what the, I guess, what above and below the line will look like. So knowing how kind of overall physics works, if you leave an object in a room, it's going to tend to go to that. Yeah. So do you just plug in? Yeah, that's another way to do it. So using logic, you can come to a solution quickly, but you could also just test, well, if I put in 71 here, so if I plug in 71, I get 71 minus 70, so positive 1. And then positive 1 times negative 2 is equal to negative 2. So our temperature is changing by cooling or going negative. So if dt is equal to, so negative 2, 71 minus 70, it's going to be less than 0. If we use instead 69, because that's 1 less than 70, we get negative 2, 69 minus 70, which is negative 1, times negative 2, which is greater than 0. So that means this we're having arrows pointing up, this we're having arrows pointing down. So above 70, we have arrows pointing down. Of course, as they get closer, it's going to be more like this. You don't have to do as fine of a resolution as this. I just messed up and did that. So then on the other side, we're going up. So all the way up here, it's going to be really steep. Because obviously if you put something that's 250 degrees, which is above boiling temp for water, it's going to be, yeah, it's going to be really quickly cooling. So we get just this. So yeah, any questions about this? Like what you would do? Oh yeah, and mark any equilibrium solutions. So this would be our equilibrium. And this would be a stable too, because both from above or below it converges down to here. So how would we use it to estimate the solution? So normally you wouldn't estimate it in this case because you're given the equation or the equations, you can quickly come up with it. But if you were just given a slope field, you would look for anywhere where you have horizontal lines. And then you determine whether it's stable or unstable, given whether these arrows are pointing towards or away. Yeah. Part E in the question. Oh, use your sketch to estimate the solution to the IPP above. Yeah, so what you would do there is knowing that your temperature starts at 30 degrees, you would trace, so at T equals 0, you'd have 30 degrees. And then it would trace like this, if that makes sense. So kind of hard to see here, but it would follow something like that. I guess, wait, no, it wouldn't go like that. It would go from here, it's already going like this. So it'd go like that. So that would be our solution. So given a slope field, I don't know if they have a good example here. Well, here's the key, yeah. What you do is you find out your initial solution, which we know is right here. And then given that, we know that if we were to solve for change in temperature there, it's 80 degrees Fahrenheit per minute. So it's something like that. So then you just loosely follow the arrows from there. I guess they don't have arrows here, but you follow the slope field. So you can do that with any situation. And so you just find your initial point here, and then you just follow the lines. Go something like that. So yeah, any other questions about this? Sorry about the mix up there also. I always assume that it's further step because I've done it so many times.
More separation of variables practice.
Yeah, yeah, true. More separation of variables practice. Do
Yes, please.
you want more right now? I don't know if I can
I'd say
find
no.
a question. Can't think of any real nasty ones off the top of my head. I can only think of real simple ones.
I can give you some disgusting ones from the WebAssign.
Yeah, do that. Give me another one. Do that real quick. Been a while since I took DiffyQ, but I remember most of the stuff from Calc 2 at least. Got a WebAssign is evil in the chat. I agree. Sometimes I hated it myself. My least favorite problems are the practice ones that just have you go through an endless amount of steps.
Especially when those steps don't mesh with how you normally do problems.
Yeah, that's the main problem that I find as a coach whenever someone's working on those. It's just, you normally don't follow all those steps. A lot of times you can skip them already, so it doesn't make sense.
Here's another one. Doesn't seem particularly nasty, but it's another one.
All right,
Um,
I'm gonna assume that it's dy dx is equal to something.
xy squared y prime equals x plus 9. So
Oh wait,
y prime.
x y squared y prime, okay.
Yep.
Okay, so x y squared d, so y prime you can rewrite as this. That's gonna be my one tip to you guys. Always rewrite it as this, just helps out in separating stuff. So then it's equal to what? 9 plus x?
X plus 9.
X plus 9, so same thing, okay. I'll just write it as x plus 9 though. Okay. So you get x plus 9. So for this, we need to get all of our x terms on the same side, and then get our y terms on the same side. So luckily, our y is already kind of together, and then our x's, we have this and this. So we want to get our dx over here anyway. So we divide by x, and then multiply by dx. So we get y squared dy is equal to, now we have x plus 9 over x dx. And this, I'd immediately recommend separating it and simplifying. So since we have a, so this could be equal to x plus, or x over x plus 9 over x. This cancels to 1. This is the quantity times dx. So now we have y squared dy is equal to 1 plus 9 over x dx. And we integrate both sides. This is our power rule. So we do 1/3 y cubed. And then always put the plus c with the dx. So here, integral of just 1 would just be x. Integral of 9 over x would be 9 times natural log of x. That's because you can simplify this to 9 times 1 over x, or separate it to 9 times 1 over x. And yeah, so now we just do our plus c. Now we have our 1/3 y cubed here. We want to get it down to just y. So we get y cubed is equal to 3x plus 27 natural log of x. And then the plus c, we can keep the same because 3 times c is still just c, because it's a constant. And now we just simplify by taking the cube root. And we get this. Oops, I'll bring it up. And there we go. So it's all about knowing how to move these terms over.
Question, how did you eliminate the 1/3 in front of the y to the third?
So y squared, when you take the integral of that, you raise the power by 1, so up to the third, and then divide by the new power. So 1/3 y cubed. Is that what you asked?
No, how did you get rid of the 1/3?
Oh, I multiplied both sides by 3, my bad. So multiply that by 3, that by 3. So 3x plus, so 9 times 3 is 27, so on and so forth. And then, of course, the plus c remains unchanged. So any other questions about this problem? I don't know how hard they'll be on the exam. But assuming is this one calculatorless? Anybody know? Do they get a calculator on this exam? No, that's what I thought. Yeah. Yeah. For the most part though, this doesn't really require a calculator like these problems. They won't do much for you except maybe help you with 9 times 3 a little faster if you need help, but the calculator is not really necessary because you just manipulate a problem. If anything, it makes you take longer if you to try to plug stuff in. All right. Well, it's 6:55. We can get ready to swap over to the next section. Feel free to stay. The Zoom meeting will be up in probably 2 minutes. Tons. So yeah, have a good rest of your day. I'm signing off. Oh, you're recording, so you